So the last section we're going to do in Unit 6 is linear programming notes. Now, linear programming, well, we're not going to do notes, but we are. Okay, linear programming, the reason this is important is because in business, what they have to do is they have to take all these different bits of information and figure out how to make a maximum profit or how to get the greatest amount of people from one place to the next. So there's a lot of different ways that linear programming is used in the business world. So that's what we're looking at. So this is a real practical approach to where you would use inequalities in the workplace. So I want to go over a couple different definitions, but I don't want to get too constrained in it. Before we go any further, I want to show you an example of what we're going to be using linear programming for. So this scenario is talking about they want to figure out how many vans, large or small. They have to talk about the cost, the maintenance, and then how can they move the most people. So this is the type of problem we're going to be doing. We'll look at that in just a second. So in your packet, we're going to be going through just a few different terms. We're going to refer to this picture when we're talking about this. So it is a method of finding a minimum and a maximum, or a maximum. Maximum if we want to find the greatest profit, how much money we could bring in. Minimum is the lowest amount of cost that it might be in order to produce an item. Value of a linear program called the objective function. So this is what we're trying to figure out. This function is going to be the profit, or it's going to be minimum, like to keep costs down. That satisfies a given set of conditions called constraints. Okay. So again, I don't want to get too caught up in this. Feasible area. The feasible area in this particular problem would be right here. Okay? So the feasible area is a set of points that satisfy the constraints. We're going to talk about what the constraints are in just a second in a linear programming problem. In other words, it is the shaded region, or where the solutions are, of a system of inequalities. So that's the reason it comes into play here. We're going to use our inequalities, our systems of inequalities, to find out. Those are going to be our constraints. So the constraints are one of the inequalities that define the feasible region. Feasible region is the shaded part in a linear programming problem. They are considered to be the restrictions. So constraints and restrictions are pretty much interchangeable, and that show the real world. Now, what we call vertex points. The vertex points are the intersections of the constraints, and remember the constraints are just the inequalities. So it's kind of like we're taking the constraints would be where the lines intersect on equations, but we can also talk about the shaded areas. So this is going to be our vertices, vertex, plural form is vertices, vertices. Okay, that's the plural of a vertex. The vertices are going to be where we're going to find our maximums and minimums. The objective function is the maximum or minimum function in which you could check the vertex points. So after we get done finding the feasible area, we're going to take the intersection points. So like if I look at this problem, I'm going to take that intersection point and this intersection point. These are the constraints. This is what we define it as where are going to be. And then we take these points, these intersections, these vertices, we plug them in to that objective function at the end. Okay, so now let's just go to that page so we can see where we actually use it. So you're going to turn 1, 2, 3, okay, get to where it says the West Hartford Senior Center is trying to establish a transportation system of small and large vans. It can spend no more than $100,000. Wow, that's going to be important someplace. That's the other thing that's kind of confusing. On these problems, it seems like there's so many numbers. Which ones do I use where? I'm going to help you with that. No more than $100,000 for both of the vans. No more than 500. No more than 500. That's for maintenance. No more than 500 for maintenance. The West Hartford Senior Center can purchase a small van which carries 7 passengers for $10,000. Maintain it for $100 a month. Large vans can carry 15,000, cost is $20,000, and maintenance is $75. It's always is weird to me that it costs more for maintenance on a small than it does on a large. But I don't know mechanics. We're not going to go there. How many of each type of van should they purchase if they want to maximize? So that's where maximize the number of passengers. And in this one, they do not give us the function. And I will tell you that, oops, oh, it's too nice a handwriting to be mine. To find this objective function, it's going to be that I find a function of x, y. And it's going to give me an equation with an x and a y. So they're going to give me a number with an x plus a number with a y. So it's kind of weird. We will know the x and the y. We'll know the order pair and we'll plug in both. But our objective function is going to look like this. So in this particular one, we're trying to maximize the number of passengers after we look at all the costs. So our function, and on some of them it's given and some of it's not, is talking about the number of passengers. So the small van, I'm going to come back to that in just a second. Let's identify the variables. So we're going to have x be the small van. We're going to have y be the large van. And I'm using x and y for two reasons. One, my handwriting, and you wouldn't be able to tell if my s was a number. The other one is that it tells us what axis we're going to be. We're going to identify what is constraining it, and then we're going to write inequalities from that. So one of the constraints that we haven't really talked about is that we're not going to have a negative number of vans. We're not going to have a negative number of vans. And so if I'm not going to have a negative number of vans, that means that it has to all be positive. So it has to be positive numbers. Okay? One of our other constraints is our budget for buying it and our budget for maintenance. Okay, now we're going to write inequalities based off this and this word problem. So if they're all going to be positive numbers, that means that the number of vans has to be greater than or equal to 0. And the number of small vans has to be y is greater than or equal to 0. And we kind of talked about that in inequalities as far as where those quadrants would be. So that's the two obvious ones. And pretty much in every linear programming problem, you're going to have those two constraints. Pretty much always going to be, and we'll end up in the first quadrant. Now let's look at the budget for buying it. Well, how much does it cost to buy the small van? Small van costs $10,000. So $10,000 for each van. Small van is X. And for each large van, it's $20,000. And what can our budget? Look at our budget. No more than $100,000. So this has to be less than or equal to $100,000. Now let's look at maintenance costs. For the small van, it's $100 per month. And for the large van, $75 per month. And remember our maintenance, it told us our maintenance can be no more than $500. Those are going to be the inequalities that we're going to use in order to determine what we can use for our maximum. Okay, we're going to identify X and Y intercepts to label. And this is one time we're going to go back to. We're not going to use slope and Y-intercept. We're going to identify the X and Y intercepts. Okay, another reason to use X and Y. And we're then going to graph, and then we're going to determine the feasible reasons, list the vertex points, and then we're going to find our profit. No, here we're going to maximize the number of passengers. Minimize our cost, maximize our number of passengers. So this will tell us in our feasible reason to minimize the cost. This will tell us down here how to maximize our passengers. Okay, maximize passengers is what we're looking for. Okay, so let's graph these. To graph X is greater than 0, Y is greater than 0, what that tells us is this axis is going to be X, and this is going to be Y, and it all has to be positive. Okay? So now, let's kind of reduce these. If we take some of these numbers out and start finding our X and Y intercepts, it'll make it a little easier too. We don't have a lot of room to do it. So if I want to find my X-intercept, remember I plug 0 in for Y. So I'm going to, if I plug 0 in for Y, and I'm going to write them as equations when I go to solve the X and Y intercepts. So to find the X-intercept here, I'm going to take 10,000 times X, and it's going to be equal to 100,000. And I'm going to solve that by dividing both sides by 10,000. Okay, Okay, and what I did is I plugged a 0 in for y, so that's the reason that is wiped out. Okay, so let's take a calculator and find out what that amount would be. So 100,000, we should be able to do this without a calculator. That's going to give me my x-intercept on this one is 10. And my y-intercept, that'd be 20,000, is equal to 100,000. Find out your x-intercept there. And then I want you to go and find the x-intercept and y-intercept for these. Go. So for our first equation, we found out our x-intercept is 10, our y-intercept is 5. For our maintenance equation, we find our x-intercept is 5, and our y-intercept is a convenient 6.66666, so we're going to use 6 2/3 and approximate where that is. So what we need to do is we need to look at how we want to divide these as far as what are how many vans. Now, luckily, notice our numbers don't go above 10. So we can actually go a little bit more than that. And we can buy up to, well, let's just go for a while. Let's start at 10 and just go and see where it gets us. Let's make sure we always label our graphs. This is the number of small vans. Whoops, can't see that. Small vans. And we're going to go that this is 0, and 1, 2, 3, 4, 5. You know how to count. Okay? And then over on this side, this is going to be the number of large vans. And we're going to go by ones there also. Okay. So I'm going to graph each of these. I like to use 2 colors just so I can see what I'm doing. I'm going to use green for the first one. So my x-intercept is 10. My y-intercept is 5. Okay, and that's for this equation right here. Okay, and straight edge, I need a longer straight edge. And we draw these are all equal to, because it can be, the line can be part of the solution. Okay, those can be part of our solution. Now what we want to do is we want to see where to shade. So it's going to be where it's less than, so it's where it's smaller. Okay, so it's going to be smaller. So for now, what I'm going to do is I'm just going to draw arrows down. The reason I'm doing that is because there is so much going on. So I'm going to draw arrows. Now let's graph the other one. Our x-intercept is 5. Our y-intercept is 6 2/3. So here's 6. We're going to say 2/3 is probably about right there. And we're going to draw that. I'm also going to mark that this is 6 2/3 because we might need that as one of our vertex points. Okay, now we want that to also be less than, so that is also going to be less than. That is also going down. So where is that the same? So it's the same inside this orange line and inside this green line. So right here and here is going to be where we will shade. Okay, now we have this vertex point right here. We have this vertex point and we have this vertex point. Okay. We also always have this vertex point. It seems kind of weird, but remember we're blocking it off from here to here. So the area we're talking about, let me see if I can get something to show a little bit. The area we're talking about is right here. It's from here to here to here to here. So it's this little four-sided, yeah, it's just a quadrilateral. It's nothing else. Okay, so that's our area. Now, that means that our vertex points, that's what we're paying attention to. Our vertex points are 0, 0, which is pretty much always a vertex point. We also have the vertex point of 0, 5. We have, that is a point 2, 4. And we also have the vertex point of 5, 0. Okay, so now what we do is we take these. Okay, let's come back up here for just a second. we have defined that X is a small van. And in order to maximize our number of passengers, the small van can take 7 people, and the large van can take 15 people. Okay, so this here tells us what our costs were going to be and how we can kind of minimize costs and meet our budget. We're going to come down here, take this function, f of x comma y, and we're going, which is 7x plus 15, and we're going to now take all of our vertex points and plug them in there to find out what which van we should take. Okay, so here we go. We're going to plug in, and we're going to start off. I'm going to come over here, and I'm going to take the point 0, 0. And I'm going to just plug that in. I'm just going to kind of indicate that's what it is. So that would be 7 times 0 plus 15 times 0. And that's going to give me 0. Okay? So this is telling us what the maximum number of people. So that's not going to be too smart. That would be pretty stupid to buy vans if you can't move any people. The next point we're going to try is 0, 5. And I'm just doing these in whatever order. Okay? So we're going to take 7 times 0. Plus 15 times 5, and that gives us 75. So if I have 0 of the small vans and 5 of the large vans, I could carry 75 people. Let's do 2 and 4. That'd be 7 times 2 and 15 times 4. And that's 74 people. Okay, so 2 small vans and 4 of the big vans, I carry 74 people. Then we have the 0.50. That would be 7 times 5 and 15 times 0. That gives us 35. So if I want to maximize the number of people, I want this right here. That means that I want to have no small vans and 5 large vans. So if somebody was hiring you to do an analysis of how to keep the cost down, but how to get the maximum number of people, you would use this in order to come up with it. It's kind of like part of a business plan on how you're going to do things. So you'd make no small vans and 5 large vans. Now, that's what maximizes the people and keeps the cost down. Now, it might be that this facility wants to have those some small vans for whatever reason. So they might decide to go with 2 and 4 so they can at least have some small vans. So this is mathematically what would be the best. Okay? Questions? Now, if you're getting frustrated and concerned, I'll tell you this right now. This is not going to be on your Unit 6 test. We are not going to have linear programming on your Unit 6 test. But it could show up on an EOC, could show up on an ACT, so it's important that we go through and do it. So what we're going to do now is I want you to take the time to go through and try to set this one up yourself. I will periodically come on and show you the different things. You're going to read through the problem, identify the variables, try to identify the constraints in words, and then we write the inequalities here. Okay, so I want you to try this one, okay, and then I'll come in periodically and show you different information. You'll see that when I come back on, you'll see that I've underlined different things and circled different things because that's how you want to always do it. You kind of are taking notes by circling things. Okay, I'm going to actually read with you. You are the new owner of a music shop in Lee Summit. Your first duty as a new owner is to create an advertising plan based on the budget available. You must figure out how many magazines. Oh, well, hey, there we go. X is magazine ads. Okay, do you see that? Y is TV ads to purchase. So you can fill that in. TV ads cost $600 per airing. Magazine ads cost $1,200 per issue. And your total budget is $9,000. So that would be part of your constraint. You're only allowed to purchase up to 6 magazines due to space limitations, and only up to 7 television ads for whatever reason. Research shows that for every magazine, CD sales increase by 150 for every TV ad. They increase by about 100, resulting in this function. Now this function just comes all the way down here. F of x is equal to 150x plus 100y. Okay, so that comes down here. That's the maximizing profit function. Okay, so you're going to now come up with those constraints. Go, try it. So you've now put in that the magazine ads are X, the TV ads are Y. Hopefully you've also noticed what the constraints are. You're going to only have positive numbers for ads. I keep on spelling that wrong. Math teacher in me. Your budget has to be less than or equal to 9,000. Oh wait, your budget is 9,000, so it has to be less than or equal to 9,000. You're also limited on the number of magazine ads and the number of TV ads. Knowing that, write your inequalities. You're going to have 5 inequalities. Try that right now. So to get your inequalities, you have to have all the ads you're only going to have positive ads is what you're going to be purchasing. You're not going to purchase a negative number of ads. So it has to be X is greater than or equal to 0, Y is greater than or equal to 0. The next one is using the budget. Has to be less than. Well, it's 600 for TV and 1,200 for magazine. So it's 1,200 for magazine, 600 for TV, and that has to be less than or equal to 9,000. Then the number of magazines was restricted also. So you have X is less than or equal to 6, and Y is less than or equal to 7. So those are what you're going to be graphing. So now you're going to want to identify your X and Y intercepts for all of these. And actually, the only ones you're going to have to worry about are these right here. So find your X and Y intercepts for this inequality right there. Go. So to find your X and Y intercepts, you're going to just remember you're plugging a 0 in for Y. So it says 1,200X is equal to 9,000. And 600 equals to 9,000. So you get X is 7.5 and Y is 15. Now, as you can see, we have some fairly small numbers once again. Once we take, even though these are big numbers, by the time we get them all down, it's pretty small. 15 is our highest. So let's label our axes next, and then we're going to start graphing. So label them and then start putting numbers in. Go. So we labeled our axes. We've numbered them. The one thing I forgot on the last one that I'm going to make sure I point out on this, and then I'll go back into the other one, is this. We always should title it, and we did not title it. This would be maximizing advertising results. That's what we're talking about, maximizing advertising results. And while we're labeling, let's go back over here. Our title here would be maximizing just what they're asking for, number of passengers. Okay, so sorry I forgot that before. Okay, here we go. Let's graph everything that we have. To graph the X and the Y, luckily we can just use our X is greater than 0, there. Y is greater than 0, there. So now let's graph X is less than 6. So X, remember, means it's going to be a vertical line. So at 6, I'm going to go just straight up from 6. And where is my straight edge? So here is that line. Okay, so now you can't see it real well, can you? So I'm going to kind of darken it, make it a little thicker. Okay, now you can hopefully kind of see it. Not too well. Y is, and on that one, I'm shading to this side. I'm going to shade to this side. And I'm just going to leave it like that for now so that